Hello and welcome back to the slow and painful process of me trying to get through the natural number game. When we last left off, I was totally stumped by the final boss of Multiplication World, in which we had to prove that A times B times C is the same. That's right, we're proving that multiplication is associative. So it doesn't matter if we do these ones first and then multiply it by this one, or if we multiply these ones first and then multiply it by this one. So we were using induction, and I think we tried A and we tried C. Let's try B, see if that helps, if I can finally figure out this one. So this step should be fairly easy. It's just anything, or 0 times anything is, let's see, multiply 0? Yep, or this is one is anything times 0 is 0. We want the other one. We want the opposite. Hang on, where is it? Multiplies. Yeah, 0 multiplied anything. 0 multiplied by anything is 0. So we'll do that. Rewrite 0 underscore multiply. Oh, we also need the other one because these are being multiplied together first. I thought it would take care of these ones, but since these ones are being multiplied first, I need to use rewrite multiply 0. Actually, I think it would be better we do that one first and then just repeat this one. Wait, nope. That took care of A times 0. Then I'm left with 0 times C on this side and A times. Okay, I guess we just do multiply 0 again, and then we reflect that across. And now we're left with this scenario, which is what was stumping me. How do I get rid of the successor n? Right, this and this are very nearly the same. If this was n instead of successor n, then I could, and this was n instead of successor n, then I could simply use this to turn this into this. But somehow I need to get rid of the successor n first and make it something else. Make it, well, I'm not sure, actually. And there's so many options now. We can add multiply. That proves that this is the distributive function, the proof of the distributive function. Which I don't think is what we need. Unless, I guess, maybe that would work on this? Or maybe it's the other, that would be multiply add, would be. Oh no, it wouldn't be, because this is B plus C, whereas these are being multiplied inside of the parentheses, so I don't think that would do anything. What else can we use? Multiply, hang on a sec. I hate it when your brain can't decide if it wants to sneeze or not. This one, what does this one do? Multiply commutative is the proof that multiplication is commutative. More precisely, AB is the proof that A times B is the same as B times A. I don't think that's what we're looking for right now. Multiply 1 is the proof that anything times 1 is itself. This looks promising. This looks like it ought to be what we use. A times B plus A. And that gets us... Now we have a plus A, which I don't know how to get rid of. Right? I don't know how to get rid of this plus A. Is there anything in here I can use in the addition tab? I don't think that's... No. Wait, what is this? A plus B parentheses plus C is the same as A times C. Okay. That's not what we're looking for, I don't think. A plus successor B. Sort of AB. I don't think that helps us either. Because before I did this, there was no addition, so none of these would be helpful. And now there's no successor anymore. Yeah, so what did we do? A times successor N times C. And we turned A times successor N into A times N plus A. Right, because the successor of N, that means 1 more than N, which means that we're multiplying A by 1 more than N, which is the same as just adding another A afterwards. So A times N plus A. If I can just get plus A on this side, then maybe that'll work out. That didn't do anything. What if we do that? So we've got plus C on this side and plus A on this side. So I don't see how we have any hope of trying to get the two sides to match with that. Yeah, I really don't know. What can we do? Oh wait, what if I use, instead of these two, I could use these two? Or will it even work? Because there should, like, you gotta imagine a parentheses around these ones. But maybe? Wait, not that. Yeah, this one. It is this one. Can I get that to affect these? No, it skips them and goes straight to here, and I assume that's because these have a parenthesis, or these have a parentheses around them. But I could... Can I switch the parentheses around? Yes. But I don't think that's what I wanted to do. Can I use... Oh, I used a space instead of an underscore. Okay, yes, that successfully, I switched these two around. I'm not sure that helps me, actually. Unless I do it again, and this time switch the third one around. Wait, that didn't help. Or did? Wait, am I on to something? By accident? I switched these two around. I wanted to get successor N and C together, but it seems no matter how I switch them around, successor N and A are going to be multiplied first. And I think that's because we only have commutative for the associative property so far. We only have commutative for multiplication. We don't have the associative. If I wanted to change the order in which things are being multiplied, I would need the associative property, but that's what we're trying to prove right now. So I don't think there's any way for me to get the successor N and A to switch to being... I don't think there's any way for me to switch it so that these two get multiplied first. But I still might accidentally be onto something here with whatever... What is this? What am I doing? Switching around stuff? Okay, that just switches it back to how it was. This switches it so that's... Wait, we have A times successor N times C. Successor N times C times A. Okay, so yeah, these are still being multiplied first. Successor N times C is still being multiplied first before it's being multiplied to A. Right, so I don't have the associative property yet, and that means I can't change the order in which anything is being multiplied. So if I try and use this, the successor being multiplied by the thing becomes the two things being multiplied together plus the thing it's being multiplied by. When I do that on this, I'm going to end up with plus A, and when I do that here, I'm going to end up with plus C. So if I have a plus A on one side and a plus C on the other side, I don't know how I can ever make this two sides match. But I think that's the only way I can get rid of the successor. There is, I tried last time, I got into... Yeah, you can turn the successor into... Or no, not this one. yeah, successor equals add 1. You can turn the successor of n into n plus 1. And last time I did that and I thought I was onto something, but then it turns out I just went into a circle and that ended up back where I started. I feel like this probably isn't the answer, but maybe I can try it. Let me think through what would happen if I... And so that's turned both of my n's into n plus 1. Whereas before I had n plus a and n plus c. But if I just have a 1 on both sides, that's better. That's right, that I can make them match if there's just a 1 on both sides. I'm still not sure how to implement this, because now we're kind of stuck. We're still stuck with n plus 1. I can't get this 1 out of here. Which means I can't use this until n is by itself. But we've still got parentheses n plus 1, which means I can't use this. Well, is there anything else I can do with plus 1s? I can change it to 1 plus n instead of n plus 1, but that doesn't seem to help me at all. This only works for addition, whereas this is the only addition I have, with the others being multiplication. So I can't move... I don't think I can move the parentheses. I'm pretty sure what happened last time is I then went rewrite 1 is the successor of 0, and we got that. And then I probably combined these so that it was the successor of n plus 0. And then n plus 0 is nothing, so I just ended up back with the successor of n, which is what we started with. But is there anything else is there anywhere else I can go from here? Is there anything else I can do with the successor of 0? Yeah, so this is what I used last time, and I turned it into the successor of n plus 0, and then I would have used the one that says n plus 0 equals n, and then, yeah, that's how I went in full circle. I don't think there is anywhere I can go from here. Huh. No, I don't think... n+1. Right, if I try and use my induction hypothesis, it won't work right now. But I just want to confirm that that's true. Yeah, no, it fails. Because I don't have this. I have this. And I don't know how to get rid of this +1. I prefer having n+1 on both sides to having n plus a over here and n plus c over here. This at least seems like I'm on the right track, more so. But I still have the same problem of I don't know what to do with this addition. I want to get it to look like this, but I don't know how. The +1 can't go anywhere. The successor n. Can I switch? If I switch these around, will this change? Right, we're still multiplying these first and then adding a. No, that's not what I meant to do. I want to switch a and n around, which... But it's putting c at the beginning, whereas I thought maybe I could switch these two around. But shouldn't I be able to? There we go. Now we have n times a plus a. Oh, and over here already we have n times c plus c. Wait, we might be getting somewhere. I can use 2 multiply. Something plus something is always going to be 2. I can use the backwards arrow to get that. No? It doesn't. Oh no, I can't do it that way. Because this is n times a plus a. Right? There's no a plus a. You have to imagine the parentheses around the n times a. And then the a is being added. There's no actual a plus a in existence here. And same with the c plus c, because this is being done first, and then this is being added. Okay, sad. Still, maybe I'm getting somewhere? Hang on a sec. Sorry, my cat was demanding things of me. If I used... I don't really see how that helps me. Well, I guess I have these lined up. A times n times c. But I've still got these parentheses. And I don't think the associative property for addition would help me here. No, it fails. It doesn't work. I do have a times n times c. They kind of look right, but it's not because of the parentheses, right? So that, I assume, will not work. No, it does not. I don't know how to get that addition out of there. I thought I was on the right track with this one. M plus m, or in this case a plus a is 2 times, right? It'd be 2 times a. But that doesn't work because this is a times n, right? It's not actually a times a. It's not actually a plus a. It's a plus a times n. I'm really stumped with what to do with the addition. I'm just trying anything now. Okay, we got back to where we started. My cat just got into the top shelf of the closet, and I don't know if he knows how to get down. So he's keeping it entertaining at least. Hang on. I have to rescue. Okay. He's been rescued. Fret not. How? I'm so stuck. I'm as stuck as my cat just was in the top shelf of the closet. Let me try a different letter again. Let's just switch it up and see if I can... see if there's... if anything will make it click for me. I mean, we're still in a very similar situation here, if not the exact same situation. Well, actually, okay, so b times the successor of n became b times n plus a times b. This whole thing got added to both sides. So we have plus b on this side and plus a times b on this side. So this is, at least to me, even more complicated than what we had last time. What to do next? Oh, but at least we do have a times b times n on this side, even if we do have the a times b left over being added on. I could at least do this. Induction hypothesis. And now we're very similar. We have a times b times n, or b times, we have b times n times a. And here we have b times n plus a. But we've got plus b on this side and plus a times b on this side. Also, on this side, the b is being added to these first before it's being multiplied to a, whereas on this side, a is being multiplied first, and then the extra a times b is being added. Hang on a sec, I'll be right back. Okay, back. We're back in unsure as ever. this would be the same as two times b times n. No, would it? No, I don't think it would be. No, it definitely wouldn't be. Yeah, okay, if anything, this one is even more complicated. Let's go back to A and see if I can figure out anything there. Nope, not that one. Or the successor of n times b times c. Successor of n times b times c. Right? It's so close to this, but we just have to figure out how to make it not the successor. What if, let's try this again. Whoops. I still don't think that's getting us anywhere. These still have to be added first. I don't think that's it. We gotta use the only option in this whole list of multiplication, what would you even call them, lemmas, that deals with successors is this one, and its opposite, this one. And we always end up with these additions at the end. Right? There's no others other than these two that deal with successors. Yeah, it has got to be one of these two. And I don't think it matters which one. It's got to be this. I'm pretty sure that's the only option that I even have at this point, unless I am already on the wrong track, but I don't think I am. Wait. Maybe? Can I distribute this C and turn this into N times B times C and B times C? I feel like I've tried that already and it didn't work. It worked! Ah! So we end up with N times B times C plus B times C. Plus B times C. Oh my gosh, that's the same one. Did we just do it? Did we just do it? N times B times C plus B times C. N times B times C plus B times C. Oh my gosh, we did it. Oh, I swear I tried this already, but I guess not. We get a message. A passing mathematician notes that you've proved the natural numbers are commutative. Semmering? Yeah, I don't know what that word means. Give me a second. Wikipedia says it's an algebraic structure. Yeah, so I'm not sure. If you want to begin your journey to the final boss, head for Power World. Alright. We did it! If you will indulge me, I'd like to do it again. So what was the final? it was this, add multiply. I had to use the distributive property. Let's go, but let's try and do B again. I'm just addicted to being stuck on this one problem now. But I want to do it again. I want to really understand it better. So we're just going to use whoops, that didn't do it. Okay, whoops. So all I'd have to do is whoops, I keep forgetting to type the whole thing. And then it's just the distributive property. That's all I was forgetting. And then we have this, and we can use this. And then I guess we do something on the other side. This might be a much harder version of what we did last time. I think last time we got a really easy induction. Should still be able to just... I'm going to use the other one now. Nope. This one. And now we want to distribute the A. Oh, and that's it. Same thing on both sides. Okay. All right. Now I guess the question is, do I want to 100% the game before I beat the final boss, or do I want to go ahead and get the final boss and then go and do all the extra stuff? I think in this case, I want to master the basics before I do the extra stuff. So let's move on to Power World. All right. This world introduces exponents. If you want to define 37 to the power of n, then as always, you need to know what 37 to the power of 0 is, and what 37 to the power of the successor of d is, given it's only 37 to the power of d. Or, sorry, given only 37 to the power of d. You need to know what 37 to the power of the successor of d is, given only 37 to the power of d. You can probably guess the names of the general theorems. Pow 0, a to the power of 0 equals 1. And Pow successor, a to the power of the successor of b equals a to the power of b times a. Using only these, can you get past the final boss level? The levels in this world were designed by Sian Carey, a UROP student at Imperial College London, funded by Mary Lister McCammon Fellowship in the summer of 2019. Thanks to Sian and also to the Imperial College for funding her. Cool. What is UROP? Hang on, I'm going to Google that. Undergraduate Research Opportunities Program? Possibly. Anyway, let's start. Alright, mathematicians sometimes debate what 0 to the 0 power is. The answer depends, of course, on your definitions. In this game, 0 to the 0th power will equal 1. See if you can prove it. Check out the POW tab in your list of theorems to see the new proofs which are available. Okay. So I assume this one's going to be pretty easy. Anything to the power of 0 equals 1. So in this case, 0 to the power of 0 will also be 1. So we'll make this very easy. I feel like there's no in-betweens in this game. It's either the most difficult problem that you're going to spend several hours just staring at, or it's like, type 3 letters and you're done. Alright. We've just seen that 0 to the 0 power is 1, but if n is a successor, then 0 to the n equals 0. We prove that here. Okay, we have anything to the power of 0 equals 1. We have this, that 0 to the 0 power equals 1. And we have that. Hang on, I feel a little bit dumb, but I'm like totally confused already. If n is a successor, then 0 to the n power equals 0. Okay, yeah, that makes sense, because 0 times anything is still going to be 0. Even if it's 0 times 0 times 0 times 0, or whatever this n is. But then it seems weird to me that 0 to the 0 power equals 1. But then 0 to the anything else power equals 0. But I guess that's just something I'll have to accept. That's an axiom we've decided. It doesn't have to make sense to me. So I think I assume we're going to use Pao successor. What exactly did that do? We went from 0 to the power of the successor of m to 0 to the power of m times 0. Okay, yeah, that makes sense. And then, now wait a minute. I see where this is going, and it's weird. Anything times 0 is 0. Wait, that did more than I thought it would. I thought it was going to turn this into 0, or m times 0 is 0, and then we would end up with 0 to the power of 0. And then that was going to be weird, because the 0 to the power of 0 is supposed to equal 1, but we need it to equal 0 for this problem. But then that's not what it did. It turned this whole side into 0. Oh, I suppose because these are together. I was thinking m times 0, but it's 0 to the power of m times 0. It is going to be 0. The whole thing will be 0. Okay. Next, we get no messages. I think the pink one is the one we just proved recently. Although 0 to the 0 power equals 1, in this game 0 to the n power equals 0 if n is greater than 0, if n is a successor. Okay, sure. We have 10 whole levels to get through. A to the power of 1. We use... Nope, not the 0. It would be... We can turn 1 into a successor, and then we should be able to use this. 1 equals successor of 0. And then we should be able to use Pao successor. And now we have a to the power of 0 times a. Sorry, no, we have a to the power of 0 times a, not a to the power of 0 times a, right? It's weird to try and say it in English, but right, you got imagine the parentheses here. This is being done first, and then the whole thing will be multiplied by a. So what do I do? This might be more complicated than I'm thinking it is, or it might be less complicated than I'm thinking it is. But do I need to use induction? Because I've got, what do I do? By anything to the power of 0 is going to equal 0, except 0 to the power of... In this game, 0 to the power of anything equals 0 if number is greater than 0. But 0 to the 0 power equals 1. Did it say anything to the 0 power? Anything to the 0 power equals 1. There it is. Okay, so I guess we use this one. Anything to the 0 power, right? So we get 1 times a, and that will be 1 multiply, or mul 1? Yeah, 1 multiply. There we go. Nice. Level 4. Okay. 1 to the power of m equals 1. The one we just proved says that anything to the power of 1 equals itself. So we're just going to use the lemma we just proved, right? Nope, it's reversed. In fact, that's what we're doing, isn't it? 1 pow 1. We're going to prove the opposite of this now. I thought that was too easy. Yeah. Okay. One to the power of m. Do we need to use induction, or am I going too complicated too fast? Because if m equals 0, then the answer will be 1. But if m equals anything else, it is true that anything... Wait, I'm a little confused. Do we know this is true? 1 to the power of m equals 1, but m can be anything. If m is 0, then the answer will be... Wait, no, I'm being silly. Of course, anything, 1 times anything will always equal 1. Still, we might have to use induction m. And so if this equals 1, if it equals 0, then that's easy. We just use pow 0. Anything to the power of 0 is 1, and we reflect. But if m is a number, not 0, a successor of n, then what? Here we go. Anything to the power of the successor of anything. Yeah, we use this one. And we get this. And anything times 1 is 1. Where is it? Multiply 1? No, we want the opposite. We want 1 multiply. Yeah, this one. Nope, I was wrong. We did want the other one. multiply 1. Anything times 1 will equal itself. Now we have 1 to the power of n equals 1. Wait, my goal at the beginning was 1 to the power of m equals 1, and now it's 1 to the power of n equals 1. We've come full circle. Gosh dang it. That's not very helpful. We just have a different letter, but it's the exact same thing. So what are we supposed to do? How do you prove that 1 to the power of anything? Oh wait, let's no. 1 times anything times 1 equals itself, but itself is what we're trying to figure out. One to the power of anything equals 1. Is this simpler than I think it is? Anything to the power of 1 says that anything to the power of 1 equals itself. No. Right, we want the opposite of this. Oh wait, no, we didn't. I always forget to read this. We did not come full circle. We came full circle with a new tool that we can use. I thought we were right back where we started, but not. I could still come in here and say, there we go. There we go. I was on the right track. But I thought I had done a whole circle. But I had sort of done a whole circle, but I was back with a new tool I could use. I guess. Okay. Note, this lemma will be useful for the final boss. A to the power of 2 equals A times A. That's what we need to prove. What can we do? I could break down the 2. Not sure if that would be helpful. Maybe it would be. Let's try it at least. Yeah, rewrite 2 equals successor of 1. Rewrite power successor. Now we have a to the power of 1 times a. We are on the right track. I know exactly what to do. We need one of these. Yep, anything to the power of 1 equals itself. Oh, and we're done. Yeah. I mean, you could add, you could... No, just, no, we're done. Yeah, that's it. Okay. Let's now begin our approach to the final boss by proving some more subtle facts about powers. Alright, so we just proved power 2. Anything to the power of 2 equals the thing times itself. Squared, you might say. Okay. Theorem power add for all natural numbers. Okay, interesting. We're adding exponents together. A to the power of m plus n equals a to the power of m times a to the power of n. It's kind of like the distributive property almost. At least that's what it reminds me of. It's kind of like the distributive property, but for exponents. So where do I start with this one? I'm guessing I need to use induction. Zero to the power of anything is still going to be Will that work? No. Anything to the power of 0 is 1, but 0 to the power of anything maybe A isn't the best option to go for, but I don't see how the others would be any easier. Maybe I don't have to use induction. Maybe I... Huh. I feel like it needs to use induction. I feel like it has to be induction. I don't know where else to start. No. Okay. It's got to be induction M. I can't make it two of them. No. But this doesn't get me anywhere. 0 to the power of anything. Right? I have pow 0. I don't have 0 pow. I have 0 pow successor. What if I go with N? I can do this. Anything to the power of 0 is 1. Whoops. Rewrite. Power 0. And now we have 1. Okay. Anything times 1 is 1. Or, no, sorry. Anything times 1 is itself, not anything times 1 is 1. Anything times 1 is itself. Also, anything plus 0 is itself. And that's that part done. Reflect. Now, oh no, we're back in one of these situations. N_1. Can I name it something nicer? I'll say with. Okay. We'll call this induction hypothesis. And I guess Z is a fine letter. It's better than looking at underscore N1 or N underscore 1. Okay, so now what do I do? In the case where N is a letter, or in this case Z, now what do I do? Wait, there is a thing, POW successor. Hello? Okay. A to the power of the successor of B. That's maybe something. Oh, I just keep typing them out without typing the proper syntax. Now we have A to the power of Z times A. I'm not sure if that's... A to the power of M plus the successor of Z. When I was last in this situation, I needed to use the distributive property, but I don't have the distributive property for exponents, because that's what we're trying to make right now. Maybe this? Now we have M plus Z plus 1, which is something. This won't work as long as this plus 1 is here. Correct? It will not, no. What can we do? I could use that to get the second one. Oh. We're really close to having this be this, but we still got this times a at the end. Z times a. Distributive property? A to the power of m times a to the power of the successor of z. Or now the a to the power of m times a to the power of z times a. Yeah, we do a to the power of z first, and then add a. I'm going to change it from z to n, because that's what I'm used to looking at. And z is kind of throwing me off. I don't know. This feels very similar to the problem that I was stuck on last time, or earlier at the beginning of this stream, the final level of multiplication world. It feels very similar, but I know that the answer then was that I needed to use wherever it was, the distributive property. Right? This was, yeah. But I don't have anything like that for this. I'm a little confused. I kind of want to just start this over. I'm pretty stuck. Induction. It would be hilarious if this didn't even need induction and I was just overcomplicated. But I'm pretty sure it needs induction. I don't think I can just rewrite it to get anywhere. Right? A to the power of m plus n equals a to the power of m times a to the power of n. Right, there's no numbers, it's all letters. In order to get anywhere, I have to make a guess about one of these numbers, or about one of these letters. We have to assume that we have to try for 0 and number. induction, if I try induction A, we get the problem that I don't think I can do anything with 0 to the power of, there's nothing I can say about 0 to the power of anything, because if m is 0, then this will be 1, and if it's greater than 0, then this will be 0, or no. Yes, it'll be 0. If sorry, if, right, 0 to the power of m, where does it say? Where is that? Yeah, here. 0 to the power of anything equals 0 if n is greater than 0. So for this one, if m is 0, then that's one thing. And if m is greater than 0, then that's another thing. I can't, like, do two inductions at the same time, can I? No, that would... hang on a sec. So from what I understand, trying to do the induction for A seems fruitless. There's nothing I can do. There's no next step. I'd have to do it for something else, like M. We can say, we can do this one, because A to the power of 0, anything to the power of 0 is 1, including 0. Yeah, so that's why that works. Rewrite pow 0. We get this one at least. We get 1 times this. Yes, there we go. Now we just have this trouble. Whoa, what's this mean? I have a cross next to my N. Maybe it's because I've already used lowercase n, and so it's making sure that I... Oh, it's because I already... No, it's because there's a different n in the equation. If I use m, though, it should be fine. Yeah, there we go. Okay, we're back to where we were. What can be done? We have an addition on this side and a multiplication on this side. So this is being done first, and then it'll be... Yeah, so this multiplication is done last. We have a to the power of n and a to the power of the successor of m, and then those two will be multiplied. A to the power of the successor. But that won't work on this side, because this is a to the power of the successor of m plus n. This will work on this side, but not on this side. Oh, we have an extra a in there, though. A to the power of m times a times a to the power of n. We have this extra a in here. What about this side? What can I do here? Should I look through here? I don't think that's the answer. The successor of m plus n. We're close to that. No. No. Oh wait, we're in the wrong thing. Right, I just did this. I don't know, I'm pretty stuck here. What to do? Right, I use this one here to change this one. Huh. Wait, we can change. We have the associative property of multiplication now. That might be able to help me. maybe right now these are being multiplied first and then these ones. Actually, I have no idea. Maybe this can come in handy. Okay. Let's start over. Are you sure there's no way that I can do anything with induction A? I'm pretty sure no. I don't think there's anything in here that says anything definitive about 0 being raised to the power of something. Because 0 to the power of 0 is 1, but 0 to the power of anything else is 0. So we cannot make any definitive statements about 0 being raised to the power of something. It has to be one of the other two letters. Unless I'm entirely mistaken with trying to use induction at all. But I don't think I am. Right, I'm pretty sure there's nothing I can do with this equation before I start the induction process. Nope, nothing. There's nothing I can do to these. No, it's gotta be induction. Oops. But then what to do? Wait, I can do I can do inductions within inductions, which is kind of scary, but maybe necessary for this? No, surely not. Maybe. Backwards arrow. Anything to the power of 1 is 1. This might not be. I might be going a little crazy here. No, this can't. This. No. No way, right? That's going a little too crazy. No good can come of this. Surely. What am I doing? I can't think of anything else. Except for trying to do two inductions somehow. Zero to the power of 0 equals 1. Or what happens if I try and... No, that doesn't do anything. I'm not sure when you even would use this. It doesn't say, like, this is the proof of... 0 to the power of 0. Okay, this does do that. It makes 0 to the power of 0 equal 1. Okay, so this one states that 0 to the power of 0 equals 1, and this one states that 0 to the power of anything else equals 0. Okay. Okay. I'm not sure if we can do anything else. I think we're back to the trouble we were at when we started this, which is that we can't make any definitive statements about 0 to the power of something. Right? We're back to that. 0 to the power of this, 0 to the power of that, 0 to the power of that. We do have this, 0 to the power of this. No, but this is the same. Or is it? Ah, man. I don't have any other ideas, but I strongly think that it's not expecting us to try and use two different inductions on top of each other. But I don't know what else I would do. hang on. Okay. What do we say? We say rewrite pow 0, rewrite multiplied by 1, rewrite add 1, nope, add 0. And reflect. And now we have to solve the case in which this is a successor. I'm 95% sure that this is the correct way to do it so far. I just really don't know what the next step is. I assume we want to make this look like this, right? It's just the issue. I don't know how to get rid of the successors. The successor of n, the number that comes after n. Okay, what options do I have that deal with successors? This has nothing to do with successors. Neither does that. This does. A to the power of the successor is a to the power of b times a, which I can use, and that will do something to this. I know I've already done this, but like this has got to be on the right track. That has nothing to do with successors. That has nothing to do with successors. This does, but only if it's 0. Alright, do I need to go to addition to get something for this? Yeah, hi, Kobe. Hello, I hear you. I feel like all this so far I must be on the right track. But now what do I do? We've got this and this. We've got this extra times a on the end. What can I do about the m plus the successor of n? Oops. I don't think that's not something we want. I don't think that helps me at all. No. No. I've tried this. Maybe I was onto something. No. Oh, well, that's just the opposite of this. I could get a 1 out of there, but I don't think... Well, I don't know. May as well try. Well, I thought I had a plan, but I did not. I think I'm going circles again. Yeah, if I finish doing what I'm doing here, I'll just end up with the successor of n again. Anything I can do with this now? The successor of m plus n. The number that comes after m plus n. How do I get you out of the way? I want to get this. I want to get this to look like this. But I cannot figure out how. Wait. That worked. Wait, that was it. That was it. I did it. Oh. A to the power of the successor of m plus n. And then we take that. A to the power of the successor of b. Yes. Okay, I'm not sure I have the brain power to fully comprehend what I just did, but I'm on the right track. I can now use my induction hypothesis, and now we have a to the power of m times a to the power of n times a to the power of m times a to the power of n times a. There's just parentheses. Right? Yes, parentheses. We don't want parentheses. We want to get rid of the parentheses. We can get rid of the parentheses like this, right? Or we can add parentheses. That works too. Yes! Ooh, we did it. Yes. Yes, 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 yes. The music gets even more dramatic as we explore the interplay between exponents and multiplication. If you're having trouble exchanging the right a times b, because rewrite multiply, this word will just keep ducking out of my head. Commutative. Swaps the wrong multiplication, then read the documentation of rewrite for tips on how to fix this. Okay. Current goal. We want to prove that a times b to the power of n is the same as a to the power of n times b to the power of n. Okay, so it's kind of like the opposite of what we just did. Induction n, anything to the power of 0 equals 1. Well, that's not it. Yep, anything to the power of 0 equals 1. Rewrite. Yep, 0. And we can just repeat that, I think. And then, yeah, we want anything. Rewrite, multiply 1. Oops. Reflect. And then we have the hard one. Now the question is, do I have the brain power to remember what I literally just did last level? We used... Well, we do have this. Oh right, we used this to get it. Okay, that worked. Okay, a to the power of n times b. That b is over here. We want to use the associative property of multiplication. What did that do? Is that what I wanted to do? That just added parentheses. I don't think that's what I wanted to do. Maybe the commutative property? What's that do? Oh, that switched. Wait, what did it switch? A times n times b times n. Not times, sorry, I'm completely mixing up my words here. A to the power of n times b to the power of n times a times b becomes a times... Okay, we just moved a times b to the beginning of that. What exactly do we want to move around then? We want to move a to the power of n times b to the power of n of a to the power of n times a times b to the power of n times b. we have this B by itself and this A by itself. I feel like at this point it's just a matter of moving things around. Wait, can I use this? Is there anything in here I can use? It's the proof that a to the power of m plus n equals a to the power of m times a to the power of n. There's no pluses in here at all, so I'm not sure if that's something we can use. I feel like we're really close. The associative property of multiplication. Can I say I want to free this B and get it with this A. Now is that commutative or associative? I thought it was associative, but that's, let's say nth rewrite three, nope, not three, four. What does that end up doing? That does something. A times B times N. No, I think we, what about 5? We have A times N. No, 6. B times N. Wait, maybe we do want to use the associative. Wait, can I use the arrow to get rid of some parentheses? I can, and I will. No more parentheses. Let's go. Okay, we're very, very close. A to the power of n, a to the power of n, b to the power of n, b to the power of n, a, b, b. We're literally so close. We just need to rearrange like this a, or this b to the power of n. That's all we need to do. Nth rewrite multiply commutative. Nth rewrite what, 3? What does that do? 4. That's not what I want. We still have a at the beginning. Nope, 6 is the last. We need what did this do? This switched the place of a to the power of n and a by itself. Wait, can I specify which ones I want? No, that's not. Unless I can? No, that's not. Unless. No, it doesn't like that. B at the beginning. Oh, this is probably where the message comes in. If you're having trouble exchanging the right A times B because rewrite this, yep, that's exactly what I'm doing. Swaps the wrong multiplication, then reads the documentation for RW for tips on how to fix this. Let's go here. This, we can reverse it. We can repeat it. Hang on. Rewrite H1, H2, a sequence of rewrites. Okay. Rewrite H at H2. In hypothesis H2, that's not what we're looking for. Rewrite H at H1, H2, change it. And 3 write 2 will change only the second x in the goal to y. Example, if you have the assumption h x equals y plus y, and your goal is the successor of x plus 0 equals the successor of y plus y, then rewrite add 0 will change the goal. I'm sorry, I don't have any more brain power, but like I'm so close. We're so close. Why does it stop at 6? That doesn't seem like the last one. There's 1, 2, 3, 4, 5, 5, 6, 7, 8. But it'll only let me go up to 6, which switches these two around. What if we change the first one to become like the second one? Then we would need... Wait, what did this do? A times n. Let's switch it to b. Now we have b in front. Now we have b times n in front. Okay, I know I'm like so close to finishing this one, but I'm gonna be done. Because I'm just getting frustrated now. I'm so close. All I need to do is rearrange what order these go in, but apparently that's much harder than it seems, and I have to decipher whatever this junk is. So, I'm done. I will come back tomorrow with more brain power. I am really enjoying streaming, even though obviously nobody's watching. It seems to me a really good way of keeping me focused. So, yeah. Bye.